All right, thank you, Allie. Hi everyone, my name is Jessica Lee. I'm the Public Program Coordinator up at headquarters, and I'm here today to talk about some important updates ahead of the 2025 heat season. So to start off, on March 10th, we officially renamed our NWS Heat Watch and Warning products as part of the ongoing Hazard Simplification Project. These changes were based on data collected during public and partner engagements, surveys, and social science research. And for these changes, Excessive Heat Watch and Warning were renamed to Extreme Heat Watch and Warning. The renaming of these products seeks to improve our communication and messaging of hazardous heat and better convey that heat is dangerous, as well as align our terminology with the Extreme Cold Watch and Warning products, as well as with the terminology that other agencies, media, academia, and organizations are already using. The Extreme Heat Watch Warning products will use a new VTEC phenomena code of XH, and the old Excessive Heat Watch Warning VTEC phenomena code of EH has been retired. And this new VTEC was necessary just to ensure that the old product names are not inadvertently used in partner dissemination systems. And then as far as colors, the colors for Extreme Heat Watch and Warning on our WAWA maps will mirror what was used for the Excessive Heat Watch and Warning, and there have been no changes made to heat advisories with this. On our public program Google site, our Extreme Heat page has links to some useful materials, such as an external outreach fact sheet on the HAZSIM heat changes, as well as a new Extreme Heat Watch Warning infographic. And then for internal use, we do have a document with just a few key messages and talking points related to these changes. And Kim just dropped a link in the chat that will take you to our Google site. Next up, I will briefly discuss the various heat forecast tools we have and how to best utilize them. So the NWS has three main forecast tools to assess heat, in addition to our traditional air temperature and maximum minimum temperature forecast. These tools being heat index, wet bulb globe temperature, and heat risk. Each of these tools have unique strengths and limitations and are designed for different audiences. And the application of each tool must be for the appropriate audience to ensure effective heat tool utilization and heat stress awareness. Starting off with heat index, I'm sure everyone is familiar with this one, but this is our flagship heat stress indicator, providing a feels-like temperature using our relative humidity and temperature forecast. Heat index is calculated for shady areas with light winds and includes 21 other parameters and assumptions in its calculation. Heat index is beneficial for public messaging as it is generally easy to understand and most people are familiar with it. However, it is important to keep in mind that heat index is not the best indicator in areas with low humidity. It is not an accurate measure of heat impacts on active individuals, and exposure to full sunshine can increase your heat index values by up to 15 degrees. Wet bulb globe temperature measures heat stress on the body and takes solar radiation into account. It also takes into account our temperature, dew point, wind, and sky cover grids. And within our forecasts, the effects of solar radiation are estimated using sun angle and our forecast cloud cover. Wet bulb globe temperature is a great element to monitor for acclimatized, healthy, and physically active outdoor communities. Examples would be the military, outdoor workers, athletes, marching bands, and in general, anyone doing strenuous outdoor activities. And is also a great tool to help guide emergency management decisions and enhance response. Some important considerations to keep in mind. Wet bulb globe temperature is highly sensitive to surface conditions. For example, if the surface is grass versus asphalt, as well as wind speed and wind fetch. And additionally, wet bulb globe temperature is not directly comparable to temperature or heat index scales, and the values can be lower than heat index or even air temperature, which may cause the values to be perceived as a lower risk. And this could also result in confusion when messaging to the general public if proper context and local guidance are not provided. Finally, we have heat risk, a color numeric-based index that provides a forecast risk of heat health impacts to occur over each 24-hour period in our 7-day forecast. It takes into account how unusually above normal the temperatures are for the time of year for a specific location. It takes into account also the duration of the unusual heat, including if there's any overnight relief, and if those temperatures are at high enough levels to pose an elevated risk for heat complications to occur based on our CDC heat health thresholds. Benefits of heat risk: it helps the general public understand what forecasted heat means for them, and it better accounts for variations in climatology and human acclimation. It is also a great tool to provide guidance for decision makers and especially heat-sensitive populations. Some considerations are that heat risk does not directly account for humidity, and it also does not have a wind component. And finally, I just want to briefly touch on the GHWO and how it differs from heat risk, as we heard some comments on this last year. So while the GHWO and heat risk are both risk indices, they are based on different parameters and will therefore have different results. The GHWO hazard risk levels generally correspond to our heat watch warning advisory criteria, which are based on heat indices. However, one main goal of the GHWO has always been to move toward a more impact-based information in yielding the hazard risk levels, which is one of the strengths of heat risk, as it incorporates those impact-based health information. Another thing to keep in mind is that while the GHWO heat index thresholds are static throughout the year, the heat risk thresholds change daily based on local climatology. So as WFOs become more comfortable with heat risk, we will be looking into how these products might better coexist. And as heat risk is still kind of the new kid on the block, I'll now move into just some reminders and best practices on using heat risk. Starting with a brief review of how the heat risk daily thresholds are derived. Here we have the annual maximum temperature thresholds for the Kansas City International Airport. This type of chart is available to you all as a visual means to see the daily thresholds for the entire year at specific sites around the country. So along the x-axis, we've plotted calendar days, and then along the y-axis, we have temperature in degrees Fahrenheit. And starting with our historical data, we have the black curve, which denotes the daily NCEI normal maximum temperatures for 1991 to 2020. And then the lighter gray curve denotes the smoothed 95th percentile, derived from a standardized period of 1970 to 2020 for all sites. This light gray curve identifies the top 5% of temperatures throughout the year for that site. And the reason we used the 95th percentile here is that during our research, we found many examples of other heat systems worldwide that leverage the 95th percentile to define extreme heat. And then the dots towards the top of the chart represent the daily record high temperatures for the station during its entire period of record. So then we can start to lay out our daily thresholds. So the yellow or minor threshold is based on the minimum mortality temperature, which is a threshold that was modeled by our CDC partners to determine when deaths from heat first begin to occur. And then for rural locations, we utilize the first percentile for those deaths in order to have a slightly higher temperature threshold to represent more resilient populations in rural areas. And as you can see, our yellow threshold remains the same throughout the year, as it is just a static threshold of when we first expect heat deaths to begin occurring. For the red or major threshold, the shoulders of the curve are flat and are derived from the 50th percentile of CDC heat attributable deaths for that location. So basically, this represents the temperature where 50% of the mortality was modeled to occur at and above this value. But that also means, keep in mind, that 50% of the modeled mortality occurred at cooler temperatures than this. This intermediate value was chosen to not overwarn, but still provide values that would make a positive difference to meeting our mission of protecting lives, property, and enhancing the economy. You'll notice that during the warm months over the summer, the red threshold kind of bumps up. And so in the warm season, when our threshold encounters that 95th percentile light gray curve, we have the daily red thresholds follow that curve, which is our way of acknowledging acclimation amongst heat-tolerant populations in the summer. And finally, we have our orange or moderate thresholds. These are an intermediate value between our red, yellow, and NCEI normals curves. The orange category represents lower temperature values that would still be of danger to heat-sensitive populations. And there's also an acclimation aspect to the orange, raising the threshold in the summer. But we do cap the orange threshold at the CDC 50th percentile of heat attributable deaths, which is our baseline red criteria, because it's likely that many of the heat deaths that occur in the summer will continue to be within heat-sensitive populations. And then you'll notice that in the fall, the flat area of the orange curve is slightly higher than it is in the spring. And this is just to represent a more resilient population that remains after the heat of the summer. So we follow a somewhat similar approach for minimum temperatures. We leverage the CDC data for the yellow threshold, but for the orange and red thresholds, we solely leverage climatological data. This is because the CDC did not find as strong a relationship between minimum temperature and their health data for us to use their model thresholds exclusively. So instead, we use the minimum temperatures to identify situations where climatologically unusual overnight heat could contribute to maintaining or even increasing the heat stress that accumulated during the daytime period. But on the flip side, we can also use the minimum temperature forecast to see where they may be low enough to instead lower that risk. Additionally, within heat risk, we do use the minimum temperatures to better account for humidity by leveraging a general correlation between elevated humidity and elevated minimum temperatures. So these charts were created for about 3,100 individual stations across the country that have high quality climate data and passed our quality control process to calculate annual maximum and minimum temperature thresholds. So with those maximum and minimum temperature threshold charts, we then use PRISM high resolution climatology grids with the point data to develop daily gridded maximum and minimum temperature red, orange, and yellow thresholds across the entire CONUS. As far as humidity, we do know that humidity plays an important role in heat impacts, especially across the eastern US. In fact, there is strong evidence to support that the 100th meridian acts as a natural divide between the humid east and the arid west. And this is also true for peak average dew point. Therefore, there was compelling evidence to support making different moisture adjustments within the heat risk algorithm for locations east and west of this divide. So our heat risk algorithm leverages a term called the diurnal range modifier, or DRM, which is simply the highest daily maximum temperature in the annual curve minus the highest daily minimum temperature in the annual curve. And we calculated this for all grid points, and locations with humid climates exhibit a smaller DRM range. So we then use the DRM, or diurnal range modifier, to find areas where we apply one of two 24-hour heat risk equations, either a dry or a humid equation. So for all areas west of the 104 meridian, we utilize the dry equation. And for all areas east of 97, we utilize the humid equation. And within the transition zone, which would be between the two thick black lines, we utilize the DRM where the DRM is less than 27 degrees, we utilize the humid equation, and where the DRM is greater than 27 degrees, we utilize the dry equation. And this was represented with the dry being the brown color and the humid being that tealy color. And so after filling in some islands in the transition zone, this results in a meandering border that roughly approximates this transition between moist and dry climates. So to create the final 24-hour heat risk value that we see on our WPC heat risk viewer and on our NDFD grids, your forecast maximum and minimum temperatures are compared to the derived daily heat risk thresholds. And we assign a value of 0, 1, 2, or 3 based on where your forecast max and min T values fall within the daily gridded red, orange, or yellow thresholds for each point. And we call these the heat impact levels, or HIL values. We then combine the heat impact level values coming from the morning minimum temperature, the afternoon maximum temperature, and the following morning's minimum temperature to create the overall 24-hour value that is used. Again, with either that humid or dry equation that we already mentioned. So for humid climates, where humidity plays a significant role in modifying the feels-like temperatures, our equation involves having the heat impact level values for the minimum temperatures on either side of the afternoon high, providing 55% of the overall 24-hour heat risk value, and the heat impact level from the afternoon high accounts for the other 45%. In dry climates, the impact to heat stress from the afternoon temperature is generally much more substantial than that from humidity. So in our dry equation, our heat impact level value from maximum temperature gets the greater weight, in this case 67% of the overall 24-hour value, and the minimum temperatures provide the other 33%. One last thing to point out is, okay, how do we get magenta days? So magenta or extreme heat risk is triggered when afternoon temperatures are very near or above all-time record values, or when there are consecutive days where both the maximum and minimum temperature hill values are in the red or major category. So just to provide a quick example of how these equations work, here we have the maximum and minimum temperature annual curves for Des Moines, Iowa. So first, demonstrating how time of year matters. So in this example, we have a heat index of 90 degrees on both June 1st and July 15th, and we have the exact same high and low temperatures for these dates. However, since June 1st is earlier in the heat season, we see that the lows of 71 and 72 would both contribute a value of 2, which would be in the orange or moderate category to the 24-hour equation, and the high of 94 would contribute a value of 3, which would be in the red or major category. So applying the humid heat risk equation, a 24-hour value heat risk of 2.45 is calculated, which is very near the upper portion of our orange or moderate category because values of 2.5 and higher are rounded up to an integer value of 3, which would be red or major. So because of the early time of year and the maximum temperature value being in the red category, heightened messaging or perhaps a heat advisory would be warranted. Now, using those exact same temperature values in the middle of July, we get a 24-hour heat risk value of 1.45, which is in the yellow or minor category, indicating that these temperatures would not be unusual for this time of year in Des Moines. Now looking at how the role of humidity can be roughly accounted for, let's say that on July 15th, instead of lows in the lower 70s, we actually had a bunch of moisture move into the area with dew points in the mid 70s, and our overnight low stayed elevated at 77 degrees, with our daytime high still remaining the same at 94 degrees. So now when we plug in our minimum temperature contributions of 3, which would be in the red or major, and still our 2 or orange for the max T contribution, a 24-hour heat risk value of 2.56 is calculated, which would be in the red or major category. So this is much higher than what was obtained when the heat index value was 95. And with in this new scenario, our heat index value would have been 105. So hopefully you can see how heat risk is sensitive to higher dew points and humidity through the use of the minimum temperature contributions. A couple of best practices to keep in mind for heat risk. Your maximum and minimum temperature forecasts are the base of your heat risk forecast. In order for forecast consistency and accuracy, it is essential to update your heat risk grids anytime you make adjustments to your maximum and minimum temperature grids. Additionally, it was noted last year that an over-forecasting of minimum temperatures, including a warm bias in the NBM, were artificially inflating the forecast heat risk category. So just be mindful of that over this heat season. If you would like to go more in depth into how heat risk works, we have a couple of great webinars from last year, an internal one and an external one that include more details about the meteorology and health data behind heat risk. Those links are on our extreme heat tab on our Google site page, so feel free to check those out for more information. Okay, so finally, finish out today by discussing how heat risk can be utilized in your watch, warning, and advisory decision making. When making your watch warning and advisory decisions, it is important to remember that heat risk is meant to serve as guidance, and that while it complements our other heat tools, it will not be an exact match with our heat index-based watch warning advisory criteria. It is also important to remember that orange heat risk does not equate with advisory, and red or magenta heat risk does not equate with a warning. When the heat risk calculate procedure is run within GFE, the following grids will be automatically loaded and generated. So first up, we have the heat impact level max T and heat impact level min T grids, and these show the individual max and min T contributions that are used in the final 24-hour heat risk calculations. These grids can help you tailor your messaging and provide additional insight into why heat risk has the overall value it is showing. For example, is a red or major heat risk value due to both the max and min Ts being red, or are the overnight lows orange or perhaps even yellow, which means that overnight temps are less impactful and messaging actions like moving outdoor activities to cooler parts of the day or opening windows at night might be appropriate. The next grid we have is the heat risk grid, which just shows the final 24-hour heat risk value. And then finally, we have the heat risk Wawa and heat risk Wawa by zone grids, which provide watch warning and advisory recommendations based on either the individual 2.5 kilometer grids or by forecast zone. So more on those heat risk Wawa recommended grids. For these particular grids, there are two different ways your office can configure them. Option 1 is to set the default color table parameters to heat risk Wawa in green, which will provide an output of advisory, warning, and consider in your recommender grids. This option is generally used in the western half of the CONUS, where we have the drier climates. And option 2 is to set the default color table parameters to heat risk Wawa _rec, which will provide an output of consider and recommended. And this option is generally used for the eastern half of the CONUS. And the reason we have these two different settings is that the heat risk approach has already proven to be skillful in differentiating warnings from advisories in drier climates, whereas in more humid climates, that capability has yet to be fully vetted. And then the east heat risk and heat index combined are likely to be useful for making your decisions. Digging a little deeper, so within the grids, the heat risk Wawa recommender uses the pre-rounded non-integer values in your heat risk grid to determine which recommendations to make, again, either by individual grid point or by forecast zone, depending on which one you're looking at. For the recommends Wawa category, the meteorologist can use local knowledge and factors to then determine the appropriate product they might want to issue. And in Western region, they do have more specific Wawa recommendations, again, due to their numerous years of development and experience with the tool. The consider Wawa category implies overall lesser impacts are expected, but heat watches, warnings, and advisories could be considered situationally. This allows for considerations of situational changes in exposure and sensitivity, such as during early season heat events or major outdoor events, holiday weekends where more people are expected to be outside, if there's a lack of air conditioning in your area, or if there's widespread power outages. Here is an example of what the recommender grids will look like under option 1. You can see the color bar highlighting the consider, the advisory, and the warning. And so indicating if the meteorologist should consider a heat advisory, issue a heat advisory, or issue an extreme heat warning. And then for the heat risk Wawa by zone output, these are determined for each forecast zone within a CUWA based on the median value within the zone. And then under option 2, you can see it's a bit simpler. We just have the recommendations of consider or recommended. Pretty self-explanatory based on what we already talked about. One common question we have heard is, what should we do if heat risk is showing red or magenta, but we are not hitting our heat index criteria for product issuance? So first, we would encourage you to investigate. Use your heat impact level max T and min T grids to see what might be causing this mismatch in expectation. Could it be related to the fact that it is an early season heat event that might warrant lowering your traditional criteria? or maybe that a lack of overnight relief may exacerbate heat impacts. We would also encourage you to look at existing criteria and just check with your partners to see if they're seeing any impacts. And could this be an opportunity to adjust your criteria to reflect the impacts? And remember that heat risk is not static. The thresholds change day by day as the climatological normals change each day. Watch warning advisory issuance is informed by expected impacts, and heat risk can highlight the potential for impacts complementing the temperature and or heat index criteria that you've already established with your partners. Another common question we get is whether or not heat products should be continued overnight. We would just encourage you that rather than chasing strict heat index criteria, it's better to limit the number of different heat alerts you issue and focus instead on overall impacts and public response. For example, during major heat waves such as the 2021 Pacific Northwest Heat Dome or the 1995 Chicago heat wave, the biggest health impacts were to older adults in their homes in the overnight hours, signaling the life-saving importance of keeping headlines running overnight. So again, you can use those heat impact level Minty grids to check if nighttime temperatures will remain dangerously high, resulting in no overnight relief. And if your overnight Minties stay in the orange or red categories, you might want to consider keeping your alerts active overnight and including targeted wording about nighttime dangers in your messaging. Looking ahead, here are some of our next steps for heat risk. So the next version of heat risk is ready for rollout. And hopefully over the coming weeks, they did just put out the tech order today for version 2.6. So we should be seeing this slowly implemented across the field. The most visible change within heat risk version 2.6 will be how and when a magenta or extreme day is triggered. One of the main pieces of feedback we received last summer from WFOs was that magenta days were triggered too frequently and did not align with their messaging. With the version 2.6 changes, we have changed the algorithm to remove single magenta days and only retain magenta of multiple days in length, or for days where the max T is very near or above the all-time record high and is also extreme in value, along with Minties also being in the red or major category. And doing a reanalysis of the summer 2024 data with version 2.6, it showed that these changes reduced magenta days by 18% across the cones. Another main piece of feedback we received from WFOs was that they questioned the utility of heat risk in humid environments. So in heat risk version 2.6, we have adjusted the way that humidity is accounted for by moving to a dynamic diurnal range modifier. So that will take into account the climatology of a location along with the actual daily forecast difference between the max T and min T values to create a ratio of both the dry and moist equations for calculating the overall 24-hour value. This will allow heat risk to account for situations such as when significant moisture advects into the western US during monsoon season or when dry air masses enter the eastern United States. Additionally, a new noise reduction algorithm will be implemented to remove a lot of the random pixelation noise that is a natural result of combining multiple noisy fields together into an index. And finally, we adjusted the cadence of the cron used to send the heat risk grids to NDFD to run 4 times a day to capture situations when an office doesn't or forgets to publish and send the new heat risk grids upon editing the max and min T grids. More details on the version 2.6 changes will be included in an upcoming national heat webinar planned for early April, so keep an eye out for more information on that. And outside of version 2.6, we're also working to revamp the heat risk viewer so it's mobile friendly, with the goal being to release that before this summer. And our team also continues to work on a probabilistic heat risk prototype as well as methodologies for heat risk in OCONUS locations. Just a couple quick resources to remind you of. We do have a heat risk help room on Google Chat that is open to all NWS employees. We encourage you to ask questions, share heat risk usage examples, or provide feedback in here. I think Kim should be dropping a link in, so feel free to join that. And just again, our Google site has a lot of great resources, including a lot of heat risk resources, in addition to information on heat index, wet bulb globe temperature, pediatric vehicular heat stroke, and general heat safety and outreach materials. So with that, that is the end of my presentation. Thank you.